All right, welcome back. This is CS, nope, not 30, 4510, L12B. This is the halting problem. So recall where we are. We proved Gödel's second incompleteness theorem that no axiomatic system can be both consistent and complete. And we're finishing an arc in history that began with Euclid, and it ends in 1936 with Alan Turing. So Turing is basically the person to have the last say on this in any significant form. Hilbert had one sort of unsolved part of his program. Hilbert's program was this group of people who subscribed to things like logicism and formalism that tried to show logic was a foundation for all of mathematics, and everything could be done through pure, meaningless symbolic manipulation. The last part was something called the Dung's problem. We're not going to call it again, we'll call it the Hilbert decision problem. Which, all it asserts is given a statement, let's say F, find a proof of F or the negation of F, right? So the motivation behind Hilbert's program was really this mechanization of mathematics, to remove all creativity, in the sense that there was some kind of computational method which, given a statement, you can always determine if it's true or false, if the statement has no free variables, right? And it's easy to express very complex statements in very concise forms. So we hoped that there was a way to, for example, immediately solve Fermat's last theorem, because we can express Fermat's last theorem in logic, right? What was it? It was like, for all n, there does not exist a, b, c, such that n greater than 3 implies a to the n, b to the n, plus b to the n is equal to c to the n, right? That's probably correct. I hope I didn't make a mistake. But that's Fermat's last theorem in a few symbols. So if you can have an automated way to prove that, then you just QED, you just prove Fermat's last theorem, all right? Alan Turing takes a course in this, and he takes a course, basically all the theorems that we just did, he also does. He does it under Paul Bernays, who I think was a physicist. And he learns about the incompleteness theorem, he learns about Russell's paradox, he learns about diagonalization arguments and self-referential arguments, and he also learns about this Unscheid-Unsch problem, right? Now, this statement is worded as, given a statement, determine if it's always true or always false. That's the way the question is worded, but Turing actually proves the opposite, that such a problem is not possible. It is impossible to determine the truth or falsehood of any statement, an absoluteness. So he gets the equivalent of like a BSMS acceptance, and he gets a little bit of a year to work on whatever he wants. So he does the following things. First, invent the Turing machine. Okay, by the way, if you want something named after you, do a really bad job naming it. He didn't call them Turing machines, of course. He called them automatic machines, or A machines for short. And that's generic enough, people are just going to call them Turing machines. There are cases where things are not named, significant mathematical contributions are not named after their authors because they did too good of a job naming it. The master theorem from 3510 is called the master theorem. Nobody remembers who invented it. But the master theorem is so powerful and so short and concise, they did too good of a job naming it. You know, I think it's done by Sachs, but nobody remembers that. Nobody cares. It's actually Merrick First's PhD student actually did this. Nobody remembers though, because he did too good of a job. Anyway, this is not important. Second, we need to know that it's good. So he invents the Church-Turing thesis. Invents the Church-Turing thesis. Right. Why? Define a model of computation. Explain that it's good. 3, define algorithm. This kind of follows from the Church-Turing thesis, right? The definition of algorithm is that which is, a language L is an LTM, to mean if there exists a Turing machine which halts on all inputs, that W is an L, if and only if, M on W halts accepts. And W is not an L, if and only if M on W halts and rejects. okay? That's the definition of an algorithm. An algorithm must be defined to be one that halts and accepts or halts and rejects. In either case, it halts on all inputs. That's the definition of algorithm he uses. And that's obviously the one we use today, because any piece of code, if your piece of code gets into an infinite loop on some input, that's terrible. That's not, what does that even mean? So the definition of algorithm is one given here, right? So there are two arguments to prove the Unscheidt-Unsch problem is false. First is a kind of counting argument. Consider this to be the set of all Turing machines. And let D be the subset of Turing machines such that D is deciders. So these are machines. A machine is a decider, again, if it halts on all inputs. So what is the cardinality of D? How many Turing machines are there that halt on all inputs?
A lot.
Give me an upper bound or a lower bound or any kind of reason. Are there finitely many?
Yes.
No. Yes. There are at least infinitely many machines that halt on all inputs. Okay? You can construct an infinite family of Turing machines, each one accepts, and think about code rather than machines themselves, right? They accept exactly one string, for example. So it's infinite. Is it countable or uncountable?
Countable.
Why?
I'm not sure how to say it explicitly, but it's because it's like natural numbers where each machine is distinct.
Yeah, I mean, yeah. Another way to say that would be the typewriter principle. Every machine has a string, and therefore is a subset of a countable set. In fact, forget the restriction on decidability. This is a subset of a countable set. These are countable by every machine has unique encoding. So actually Turing uses the term Gödel numbering. Today we just do encoding. Every Turing machine may be encoded into a string, or by a Gödel numbering into a natural number, right? So in fact, there are as many deciders as there are natural numbers. Okay? What is the cardinality of sigma star?
Infinite.
Yeah. Countable or uncountable?
Uncountable.
Still countable.
Still countable.
Why? You can lexicographically order the elements. What is the cardinality of the power set of sigma star?
Infinity, but
Countable or uncountable?
countable.
Uncountable. Cantor's theorem says for any set A, the cardinality of A is strictly less than the power set of A. Right? So in fact, if sigma star is countable, then the power set of sigma star must be uncountable. So what we can say here is that the number of deciders is strictly less than the number of problems. There are more languages than there are deciders for them. There's only countably many deciders, but there's an uncountable number of languages. So in fact, there must exist some languages that have no decider for them. The first argument is a counting one, right? In fact, he actually does something slightly more precise. He considers Turing machines that take no input and print the digits of a real number. The reals are also known to be uncountable, and Turing machines are known to be countable, right? Because they're string descriptions. So the Turing machines are actually less than the number of problems or real numbers. So there are simply too many problems than there are answers. So there are many more problems than algorithms to solve those problems. The number of algorithms is countable. The number of problems is uncountable. So there certainly must exist problems that have no solution. So first off, the Unscheidt-Unsch problem is false. There exists a language that is undecidable, is what we're going to say. There are things that are not in LTM, right? Also, important to know how this is conditioned upon the Church-Turing thesis. The Church-Turing thesis is this rigorous argument in favor of the Turing machine being a good definition. But among those is the finite nature and description of all the parts. We only get to say this is there's countably many Turing machines because each Turing machine is finite in description. But each Turing machine is finite in description is conditioned upon the fact that the Church-Turing thesis is logically sound. Because if it wasn't the case that the Church-Turing thesis was logically sound, and an infinite description Turing machine was a good definition of algorithm, then this would not be true. Well, we know that's not true. So observe how there's conditions on that, in some sense, right? Questions on the first argument? Yes?
The power set's uncountable because it's an infinite set of
Yes.
infinite.
Exactly.
Okay.
You could just take Cantor's theorem here as fact if you want. Yeah. So that's the first argument of the first kind. But this may not be fun. So what he does instead, he also makes an argument of the second kind. Oops. This is a non-constructive argument because it doesn't give a specific problem which is unsolvable. Turing later does this, and now he doesn't give this exact problem, but we're just gonna say he did. Let halt be a language. It is a set of strings of machine word pairs such that M halts on W. So what this is the halting problem. This is a language. This is a set of strings. The brackets mean a string encoding. So this is a pair of strings, a piece of code with an input. Now, does the code halt on that input? That is the question that is to be solved. We can prove that such a language is undecidable. What that means is there is no decider for it. Any algorithm that solves this problem cannot halt on all inputs or do it correctly. So there are problems that are unsolvable. Oh, is that you? Yeah, push. You can push, 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 push. Push, 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 push. Oh my God, he's trying to turn. Hello? We're in the middle of the halting problem. Okay. Where were we? Whoa. Oh yes, okay. Assume to the contrary. That halt is decidable. As in the case that there is an algorithm for halt, something about it halts on all inputs, okay? So there exists a decider, D, don't call it H, for halt. Halt, this decider H takes on two inputs and always halts. So this is a decider. That means it halts on all inputs. Somehow this can be determined. By the way, if we want to prove a problem to be unsolvable, the only argument we could really make is in the contrary. We could not really do a proof by, anything except a proof by contradiction if we want to show the non-existence of something. Because to prove that, you could assume it exists and then derive some inconsistency. There's no way to argue that no algorithm exists without contradiction. I'm not exactly sure how to do such a thing. If H exists, consider we construct machine D as follows. D on input, let's say X, will run H of X on X. And if it is true, it'll loop. And if it is false, it'll halt. So let this be some pseudocode to illustrate a Turing machine D, which is built around H. If I were to give you another picture of this, let this be a machine H. H has two inputs, an M and a W, okay? It has two outputs, a yes or a no. H always halts. We construct D around H as follows. D takes on a single input and wires it to both inputs of H, okay? If H accepts, let's call this the yes and the no. If H accepts, we loop. Okay? If H rejects, then we just immediately halt. So, assume to the contrary H exists, then so does D. All we're doing is taking D and building it upon H. Okay. What is D if we were to run D on its own code? So we're going to take a machine and run it on its own code. There's nothing controversial about this in computer science. Why not? There are compilers that compile themselves. Every language, every good language at least, is bootstrapped in some sense. So somehow the C compiler is written in C, and I'm sure this is true for other languages. There is no problem of taking a machine and running it on the input of itself. There's nothing controversial or preventable about this, in fact. So we know that if you take a machine and a word, and you run the machine on the word, one of two things must be true. It either halts or it loops. Every machine either always halts or always loops. So we have two cases. If D on input of its own code halts, we may trace that backwards. If D halts, what do we know happens? This halt statement must be hit, right? If it halts, we trace back the wire, and we know that this was hit. So we know that H on input of D and D rejects. Why? Because this wire is hit, right? But if H on input D, comma D rejects, what do we know that H is supposed to do for us?
It's supposed to decide whether the halt, right?
Yeah, H is supposed to be a decider for the halting problem. So on input M and W, it tells us if M accepts W. So if H on input D, comma D rejects, that means that D on input D does not halt on D. So that means this loops. So if D on its own code loops, then it halts. Sorry, if it halts, then it loops. That can't be the case. It can't halt and loop. So suppose that D on input D loops. If it loops, well, where in the code can any looping occur? We assume that H is a decider, so there's no infinite loop in here. That's the only case an infinite loop can occur. So we trace back the wire, we see that H on input of D comma D accepts. But by the definition of H, what do we know if H accepts D comma D?
Loops.
Yeah. No, sorry, the other way. Sorry. If H says if H accepts M and W, then it says M halts on W.
Oh, so it says it doesn't loop.
Yes. Yes. So D on input D halts. So D on input D halts if and only if D on input D loops. Contradiction. H cannot exist. So that's all the halting problem is. We've proven the existence of an undecidable problem. There is no decider for a problem, for if there were, construct D and then run D on its own code, you'll reach negation. You'll reach a contradiction, in fact. What's the name of this proof technique?
Diagonalization.
This is a proof by diagonalization. It's the same technique. It's inspired by Cantor, who took, Russell came from Cantor, Hilbert came from Russell, and now we see Turing came from Gödel. I got that order mixed up, but something like this. It's the same argument. And so this is passed along to, well, let me kind of illustrate why it's diagonalization. You have D is used in two ways here, and in both a semantic way and a syntactic way. First, it uses some string to be evaluated at, but it is also a machine which is doing the evaluating. It is something that is a point of evaluation and also to something evaluated at. So if you were to suppose you were to encode the machines here, M1, M2, like this, and you were to encode here the description of such machines, M1, M2, right? And consider whether or not each machine halts on the description of each other machine. This would fill in a table. If D exists, then D is somewhere here, and the description of D is also somewhere here. So the question is, what happens here? Right? This is kind of illustrated in the table way, right? I think Alan Turing wrote this paper, he shows it to some people, no one can review it because he invented computer science. No one knows what he's talking about. So it gets passed along. I think the first person to actually review it in any serious form is von Neumann. Von Neumann genuinely cannot believe that the argument is this simple. And that's all was really needed is the diagonalization is not itself necessarily like big. It's a very simple argument, especially when you are used to constructing diagonal arguments. If you are someone who's working in this area, a logician, you are very familiar at this point, 1936, with diagonal arguments. Self-referential arguments are very well known and very well established. But what was really Turing's contribution here was not necessarily the diagonal argument, but was the definition of algorithm. That was really what was contributed here, right? Are there any questions on just the halting problem so far? Now, we mentioned by the Church-Turing thesis that computation is supposed to be formalized in the notion of a Turing machine. And similarly, deductive reasoning is supposed to be formalized in the notion of logic. So you have your modus ponens and so on, your axioms of comprehension, whatever. It is the case that logic is a formalization of the intuitive notion of deductive reasoning, and that the Turing machine is a formalization of the intuitive notion of computation. But what really is the difference between thought and computation? Because these are both mental processes. It turns out really nothing. And in fact, the notions of undecidability are incredibly intimate with the notions of incompleteness. And these are all, the Gödel's incompleteness theorem in some sense is identical to the halting problem, at least in a useful sense. So let's prove, you can in fact take, we don't have to do Gödel's argument that we did this complicated shim of discussing an object into the meta language and whatever, because the Turing machine kind of allows you to just run it on its own code. That's not preventable by anything in the thing. So in fact, you can take the following as a theorem. If Principia Mathematica is consistent and complete, then halt is decidable. Now we know that halt is undecidable. We know that the halting problem is undecidable. So what that really means in the contrapositive is that if halt is undecidable, then Principia Mathematica is not consistent and complete. So in fact, the halting problem implies, as an immediate corollary, Gödel's incompleteness theorem. That's what we're going to prove next. There's a deep connection between these two ideas, right? So and again, Principia Mathematica could be any such system that has this sufficient arithmetic. Let PM be consistent and complete. We give a decider for halt. The decider works as follows. H is going to be on input m comma w. Okay? And we want it to halt on all inputs and return a Boolean. True or false does m halt on w. So what we're going to do is build a well-formed formula phi of m comma w x. Okay? Now what is this? This should be a formula such that phi of m comma w with on input x, there exists an x, is true if and only if m halts on w. Okay? Now, how does this construction actually work? This is nothing actually very, it's a bit complicated, but it's not in contradiction with the proof. It is simply, you use the sufficient arithmetic to create a formula such that you can determine if m halts on w, okay? The way it works is that this x is really a encoding of a computation history. It's a sequence of configurations of the machine on the word. So the formula just kind of loops, it's not a computer program, it's a formula. But it just kind of like checks the formula, checks its input, x. And it checks like, is this a valid computation of M on W? And does the computation terminate? Those two things can be checked by a formula. Now, construction of such a formula is where the sufficient arithmetic is required. It does require the additions and multiplications, it turns out. And it's a bit complicated to do, but you could do it. Do you believe me? Okay. For P in sigma star, lexicographically, if P proves exists X, 5 gamma of X, so it's 5m, if P is a proof of this statement, except if P proves it is false, reject. Okay, so what we're going to do is have an unbounded for loop here, okay? This is going to consider all possible strings, and it's really going to consider if this string is a proof of this. And by the way, determining if a string proves a theorem is not controversial because we mentioned you can just check if P demonstrates right? This demonstrates relation is definable. So in fact, determining if something proves something is easy. It's algorithmically fine. You check the proof figure, you check the last line, all good. But we have an infinite for loop here, right? So we need to argue, first off, H is correct and H halts on all inputs. So since Principia Mathematica is consistent and complete, there exists a proof of either phi or of the negation of phi. Right? Because we're consistent and complete, it's either the case that M halts on W or M loops on W. One of those is absolutely true. But by consistency and completeness, it must be provably so. So, the required proof P exists. So the loop always terminates. This is not an unbounded loop because it can always find, the P always exists by consistency and completeness, so we always find such a P. So the loop terminates. Therefore, H decides halt. Done. Questions on this one? If you're consistent and complete, you can decide the halting problem, but we just argued you cannot decide the halting problem, therefore you cannot be consistent and complete at the same time. It was that easy. Because if you were, just search the proof space for the proof, and if it must exist because you're consistent and complete. So once you find the proof, just print it, that's the proof. Well, you don't even need to print the proof, just like, okay, I found the proof, then we know it accepts. Now, let's suppose we weren't working in such a proof by contradiction like this or anything. Why doesn't this actually work to decide halt? Like, you can actually just build this code right now. What stops this from running in the real world? Like, if at all, if anything. And here's the answer. If M halts on W, it does so provably. Why? Yes?
You run W on M and it halts.
Yes, but why does it do so provably? Let's say M does halt on W. What does the proof of that look like?
Would it be walking through the process of M on W.
Exactly, exactly. The history is finite. So you could say, if I were to pretend it's a paragraph proof, I would say the first configuration of M on W is this one. Then if we apply delta, the second configuration is this one. And then if we apply delta again, the third configuration is this one. And then the fourth configuration is this one. And then the final configuration is this one. So the proof is literally just the computation history. The sequence of steps is the proof. So if M halts on W, it does so provably. But we know that if M loops on W, it cannot do so provably, otherwise we could decide the halting problem by searching for the proof of it. So if M loops on W, it may not do so provably. So there exists some M and some W such that M loops on W and there is no proof it does. Sometimes you can prove a machine is stuck in an infinite loop, right? Sometimes you can syntactically look at the code and be like, while true. Oh, let me delete that line of code. Sometimes you can do that, but you can't always do that. So there must exist a machine word pair such that M is stuck in an infinite loop and you would never know it. You have no idea of knowing if it's ever going to stop. You cannot prove it's going to stop. Now, if it does stop, you know it does. So basically, like, here's a terrible woo-woo explanation of this. If something in the future becomes the present, you know it happened. But if it's still in the future, you cannot determine it yet until it becomes part of the present, right? Or at least in the past. If it's already stopped, you know it did stop. But if it hasn't stopped yet, you don't know if it ever will. That's kind of a way to think about this. But we see a deep connection here between the notion of undecidability in the sense of Turing and the notion of incompleteness in the sense of Gödel. These are really corresponding to the same thing. Gödel, though, is talking about logic. Turing is talking about Turing machines. He's talking about computation. But they're the same thing, right? We'll investigate this idea, what does it mean for something to be undecidable, very rigorously in the next few lectures. But this is now like a turning point in the course, right? We gave pumping lemma arguments to prove that a DFA could not be a good model of computation. We gave pumping lemma arguments to prove context-free grammars were not good arguments of good models of computation. We had to prove that some language was not regular and some language is not context-free. And although the Turing machine is a great model of computation, we can still give an argument that there exists something which is not decidable by a Turing machine. And again, by the Church-Turing thesis that implicates us. There is no human, a human cannot in general determine if a machine halts on a word. That implicates us. So there's deep philosophical connections between these things because there are problems that we cannot solve. We can, not unanswered, but unanswerable, right? Questions on this argument so far? Okay. Now, suppose that you don't, you're not totally convinced by Turing's definition of an algorithm, right? The definition Turing gave of an algorithm here is that M must halt on all inputs. And let's say that you are an art major, you're a highly creative type, and you are not convinced. Because you may allow a machine, maybe you want an algorithm to not just halt on an input, but you maybe allow an algorithm to be broken, in the sense that it loops some of the time, right? So let us generalize this definition of an algorithm to an arguably worse definition, but perhaps a more general definition. We say that L is in L star TM, and this is known as, well, these are known as the decidable languages, right? These are known as the recognizable, or semi-decidable, or recursively enumerable. But we say that W is in L if and only if M halts and accepts. In contrast, if W is not an L, we say that happens if M halts and rejects or loops. So if the answer is supposed to be wrong, we actually allow the machine to get stuck in an infinite loop. It can plead the fifth if the answer is supposed to be wrong. This is the definition of a recognizable language, okay? And this is a more general definition than this one. Certainly every decidable language is recognizable. But how much more powerful is such a class? It turns out that halt is actually recognizable. There exists a semi-decider for it. Give me an algorithm that semi-decides halt. Yeah.
Would it be after a certain amount of tries or input, it determines that it's not possible?
I can never determine if it's not possible,
Or
but let it determine if it is possible. Let's say M does halt on W. How can you determine that?
it'll halt, you can run through the process.
Yeah, so here's the decider. Here's a recognizer. We'll call it rec for halt. On M comma W, simulate M on W using the universal Turing machine. Now, if, let's say, if it halts, accept. Okay. This is not a very good Turing machine because it can get stuck in an infinite loop. If M halts on W, this line of code will advance to the second line. So if M on W halts, we accept. In fact, I don't even need it like this. I can just say accept. Right. Now, if M on W gets stuck in a loop, then this recognizer also gets stuck in a loop because this line of code will never finish. So it never accepts. So this gets stuck in a loop if M halt loops on W, but if M halt, accept or reject, then we get advanced to the second line and we can accept. So this only accepts if M halts, and this never rejects, but if M loops, then this loops. This is an example of a recognizer. So it appears to be the case that we can at least half decide halt. Halt, sure, there's no decider for it by a diagonal argument. Maybe that's too strict of a definition. Can we not, what's the problem with just letting the definition of algorithm be recognizable? Two things. How many recognizable languages are there? Countably. Yes. Each recognizable language has a Turing machine for it. Maybe there's more Turing machines than languages still. There's a little bit of an injection, surjection stuff you gotta do. But each of these still has a countable object to describe it, which is the Turing machine. These are still Turing machines, right? Well, language is decidable, recognizable by Turing machines. So in fact, there's still countably many of those. So there's still uncounted problems, so the counting argument still works. But can we find an example of a language which is not even recognizable? Turns out, yeah, there are languages that are unrecognizable. In the sense there's not even a semi-decider for it. We'll do this in more detail in the following lectures, but let's illustrate that there at least exists no recognizable language. An unrecognizable language that's constructive. Let's do two lemmas. First off, L is an LTM, it's decidable, if and only if its complement is decidable. Okay? Why are the decidable languages closed under complement? Again, decidable halts on all inputs, accepts and rejects. Yes?
The complement of it is still decidable because similar to how we construct the halting, we just simply negate the outputs and we still be able to decide.
Control F, return true with return false. Let this be a decider. It takes as input W and accepts or rejects, right? Consider a decider for the complement. It's called decomplement. It also takes as input W. It just wires it to that decider, and then it flips its own outputs. Control F, return true, return false. Just take the machine and surger the accept and reject states, just swap them. That is obviously a decider because this is a decider. This halts on all inputs, so does this. This is a programming intuition, right? You believe me, if the machine halts on all inputs, there exists a machine that halts on all inputs for the complement. Okay? Let's prove one more quick little lemma. If any language and its complement are both recognizable, then L is decidable. So if a language and its complement have recognizers, then the language has a decider. Let L and L complement have recognizers. Let's say R and R complement. Now this is an abusive notation because it's not the complement of R, it's the machine constructed for the complement of L. But it's a recognizer, which means if it's in R complement, L complement, it accepts, and not, maybe it gets stuck in a loop. Here's what you're gonna do. Build this R here. Put this machine here. Let this machine be M, and we want M to decide L. Okay? So what we're gonna do is R and R complement are recognizers. That means they don't always output no, because sometimes they get stuck in a loop, but they do always output yes, right? So what do you know if R accepts? By the construction of L complement, R, and R complement. If R accepts, what must be true? Yes?
That L accepted it?
Yeah, like, so if W is an L, R on input W accepts. Always. It never gets stuck in a loop by the definition of recognizing, right? So we want M to accept. Okay? If R complement accepts, what do you know? Yes?
I may be skipping a step, but that means that it's decidable, the language, because, or no.
Well, there's going to be a programming detail we have to finish. If R complement accepts, what do you know about W? Let's say W is run in R complement. So if R complement accepts, what do you know must be true about W?
W is not an L.
Yes. W is in fact an L complement, which means it's not an L. So there's a recognizer for it and a recognizer for the complement. So if the complement machine accepts, we know to reject. Now, what are we going to do to these machines? We're going to run both machines on the input. Small problem. How do you run, like, it's not the case that both these machines halt because they can get stuck in infinite loops, right? So how does M run R and R complement? Kind of a tricky question. And the answer is a little bit of programming. It can't run them serially, right? It can't say run R and then run R complement, because it could be the case that this is stuck in an infinite loop, right? Then you would never run here to know it rejects, to know if this accepts. So what you do is you do something called dovetailing. Dovetailing is where you can take a computation and through an alternating sequence of steps, you can simulate two machines simultaneously without avoiding any of this infinite loop problem. What you do is you write both machines on the tape or whatever, and you say, okay, run that for one step. Then I run that for one step, and then I run that for one step, and I run that for one step, and I run that for one step, and I run that for one step. And you go back and forth over and over, slowly advancing each. Now, if we know it must be the case that W is an L or W is not an L. One of these has to be true for every W, every L. So one of these machines will accept eventually. So this M will eventually halt because one of these will accept. But you have to march them in a slow way. It's a little complicated programming-wise, but that must be done. So we see that we've proven the second lemma here, that if L and L complement are recognizable, then they are decidable. Now, why do we care about that? Halt is not decidable. We proved this, right? We also know that halt is recognizable. give you a picture. We know halt is here, right? What do you know about halt complement? And in the string sense, it's just a complement of the set halt, where halt is the set of machine word pairs. So in fact, halt complement also technically contains malformed strings, but that's not particularly important. What would you conjecture about the decidability or recognizability of halt? Yes?
It's recognizable, but not decidable.
Sure. So suppose it is recognizable. If it's recognizable, and its complement is recognizable, apply theorem 2 we just did. Let's suppose halt and halt complement are both recognizable. What do you know is true about halt?
You can make a machine that does lemma 2.
Exactly. So that's a decider though for halt. Contradiction. So halt complement is in fact not recognizable. Sure, you have a semi-decider for halt. You could never have a semi-decider for the complement of halt. Assume to the contrary that halt complement is recognizable. But we gave a recognizer for halt, and we know that if a language and its complement are both recognizable, that would imply that halt is decidable. Contradiction. So what that means is halt complement cannot even be half decided. It's over here somewhere. The complement of halt is even harder to decide than halt. It's even further from being definable by an algorithm. So what all we're really saying is here is like, even if you generalize your definition of algorithm to contain these terrible semi-decidable languages, which you shouldn't, by the way. The definition of algorithm should be this one, which halts on all inputs. But even if you suppose you made such a generalization, it doesn't even really matter, because you can still find a language which is still not even recognizable. Undecidable problems exist, fine. But even worse, unrecognizable problems exist. There are problems which cannot even be halfly done in a half-hearted way. Questions on this? Oh, okay, I'll give you one more fun fact. And this is not something that is like very important or like anything like that. So we return to the questions of axiomatic set theory, and one of the last real things proven in this era was something called the continuum hypothesis. The continuum hypothesis states that there does not exist a set C such that the cardinality of C is strictly between infinities. Recall that the natural numbers are countable. The power set of the natural numbers are uncountable, right? The question is there an intermediate? So we know that there's at least a countable infinite number of infinities. Second question, is there an uncountable number of infinities? We know that, so the first question is are the cardinal numbers dense, right? So again, this corresponds to Aleph 0, and this corresponds to Aleph 1. Is there something like Aleph 1/2? Is that a thing? Can you do that? It's complicated. So what happened is Gödel, in 1943, I think, 43? He proved that ZFC, which is the modern axiomatic set theory, cannot prove the negation of the continuum hypothesis. So you cannot prove that continuum hypothesis is false. Cohen, in 1960, I think, proves that ZFC, he invents this complicated technique called forcing. So if something is not, if you prove something is not false, it ought to be true. But he proves that ZFC cannot prove the continuum hypothesis. So unlike Gödel's sentence where something is true and something is false, the continuum hypothesis is in fact neither. It's said to be independent. You may assume it or its negation for free and not construct a contradiction in axiomatic set theory. You either take it as an axiom or you don't. It doesn't matter. Nothing changes except any logical deduction that can follow from it as an axiom. So it doesn't really matter if you assume it to be true or not. Now we don't constructively have a set that looks like this behavior. We can't prove it because existence would confirm the continuum hypothesis, and we also can't prove that no such set exists because that would deny the continuum hypothesis. So it's completely out of reach. We can't touch it. We can't do anything to it. Unlike the construction in Gödel's incompleteness, where we have a sentence which is true but unprovable, we're at least certain that it is true, but not provably so. Here we have a sentence that we cannot even determine its truth value, because it's both in its negation or unprovable. So we can't, it's somewhat farther than the Gödel sentence in some sense, right? I think Paul Cohen had to invent something called the method of forcing, which is quite difficult. It would take like 6 weeks to actually go through the proof. And it was the only time a Fields Medal has been awarded in logic. And, we're still seeing that there are statements that are extremal and about systems that are not. This is not really a self-referential question, but it is a foundational question in the sense it's about the axioms. But as we see, we can't say anything about it or its negation. It doesn't even hint towards whether it ought to be true or not. We have no idea, we don't know. So, questions? All right.